So last time we talked about endurance limit modifying factors, and in particular we talked about how do we convert from sigma E prime, which was our endurance limit for the Moore experiment, Moore test specimen, to the endurance limit for any mechanical element. And we said, well, all we have to do is we have to multiply our endurance limit for the Moore specimen with these endurance limit modifying factors. We had started by going through them. We had discussed Ka, which is our surface factor, and that's where we had ended. And so let's continue going through those endurance limit modifying factors. And the second one is your geometry factor. And remember, physically what these parameters represent is how different is your actual mechanical element from your Moore specimen. And that needs to be reflected in these endurance limit modifying factors. So the first one was focused on how is the surface quality different. The second one is focused on how does the geometry differ from the Moore specimen. And the geometry factor is actually a function of the loading. And again, all these parameters are sort of empirically determined, right? So there isn't necessarily any physical reasoning for that other than that experiments were conducted, and based on those experiments, conclusions were drawn, and they're cast in this form of endurance limit modifying factors. And so we say that Kb is equal to 1 if there's axial loading. So if there's axial loading, it doesn't matter that our mechanical element is different from the Moore specimen. Our endurance limit is not going to be affected by that because Kb is going to be set equal to 1. Remember when we talk about loading, in this case we're always talking about dynamic loading, right? We're not talking about static loading because it's fatigue loading. We're talking about dynamic. If we have torsion or bending, then Kb is going to be a function of the dimension of that mechanical element, which I'm going to call d. And how it is a function of those dimensions is shown here in the formula sheet. All right, so Kb is 1 for axial loading, is again mentioned there. If you have bending and or torsion, then we calculate Kb using these formulas. The first two are when your dimension is given in inch, and the second one, or the second set of two, is given when, or is used when your dimension is given in metric units, in millimeters. And again, this is an empirical formula. You can't convert millimeters to meters and plug it in this formula, right? This needs to be plugged in millimeters. That's the only way this works. So if your dimension of your shaft is between 2.79 and 51 millimeters, then D is going to be plugged in this equation in millimeters, and you'll find Kb. And if it's between 51 and 254 millimeters, then it gets plugged into this equation and you find your Kb. And again, you have to plug it in millimeters. And so what we can write here is see formula sheet. All the equations are there. And plug values in millimeters. Sometimes our shaft is non-rotating, or even non-circular. These values, these equations that you see here, are only for rotating circular shafts. So if we have a non-rotating or non-circular shaft, we need to do one little tweak before we can use those equations, and we need to sort of calculate an equivalent diameter. And so in case we have a non-rotating or non-circular shaft, we first calculate an equivalent diameter. Which we'll refer to as the equivalent. And so there's the theory of how to do that is explained in the book, and we're not going to go into detail. We're here going to only deal with two types of non-rotating, non-circular shafts. And the first one is a rectangular cross-section. What if we have a rectangular cross-section with width B and height H? Then our D equivalent is given as, and it's in the formula sheet there, 0.808 B times H. Of course, that also works for square cross sections, right? Just set your D equal to H, and then your equivalent diameter is going to be 0.808 times the side of your square. And then the second one is a non-rotating circular cross section. So I'm going to draw a circle here, and I'll write that it is non-rotating. And the equivalent diameter there is, and this is lowercase d, is then 0.37 d. And you can see intuitively why, if the shaft is non-rotating, we have to account for that in our fatigue calculation, because say that this shaft is non-rotating, okay? Let me draw a shaft over here. Supported in two bearings, and I got a transverse load F, and first the shaft is rotating. Then you see that when your shaft rotates, you'll expose each fiber of the shaft to an alternating stress, and each fiber of that shaft is going to see the same alternating stress depending on how far it is from the neutral line, right? However, now let's assume that this is not the case, that this is not rotating, but that this is, for instance, F sinus omega t, then you have always the same fibers that see the same level of stress, right? Again, if this were to be a cantilever beam, and you were to load this, or maybe I should convert it into a cantilever beam, even easier. And you see now that my maximum stress in case of the rotating element is going to be some kind of circle around the contour of that shaft, but in this case my maximum stress is not going to be a circle. It's going to be some region at the top and at the bottom of my shaft. That's where my maximum stress is going to occur. So you see that the stress distribution in the shaft is different for different loading conditions. And as such, or for different situations, rotating versus non-rotating. And as such, we need to account for that in our calculation of the fatigue failure. And so this is build your intuition. And if you're interested in learning how these and you should do the reading, in the book it explains nicely. It's not very difficult how you derive these equivalent diameters, but it's interesting to see how it's done. Okay, that's KB. let's talk about KC.
Who
Who has a question?
Are we ever going to have a hollow shaft? So you got an inside and outside diameter?
Yes, and so in case you have a hollow shaft, it does not matter compared to a non-hollow shaft for your fatigue failure. The only thing that matters is whether it's rotating or non-rotating. And the story is again the same. It all depends on where your maximum stress occurs. And for a hollow shaft versus a solid shaft, the maximum stress occurs exactly at the same position in both cases, where it's rotating and where it's not rotating. So of course it's going to matter in terms of how big do I need to design my shaft. If I have a solid shaft versus a hollow shaft, I've got less material, so it's going to be less strong, right? But in terms of the way the calculation is done, that makes no difference. It's a good question. All right, KC. KC is the loading factor. And pay attention for 20 seconds right now, if this is the only 20 seconds that you would pay attention during the lecture, because this question comes back a gazillion times during the semester typically. What to take KC, okay? So KC is equal to 1, unless there's a very good reason for it not to be equal to 1, okay? Almost always. If we scroll down in our formula sheet, you'll see that what it says there, KC is equal to 1 for bending loading, and what that means is pure bending. It's 0.85 for axial, and again that is simple axial loading, so pure axial loading without bending, without torque, and then 0.59 for torque. So if you ever are in a case where there is pure axial or torsion loading, which doesn't occur very often, then you can take KC equal to that value. If you have combined loading, which is almost always the case, then KC is equal to 1. And we'll account for the different types of loadings, and you'll see that we'll do example problems. We'll account for the damage that each different types of stress does to the pure element in another way, not with KC. So if you don't know, it's always safe to assume that KC is equal to 1. Okay? So if you doubt, if you're not sure, take KC is equal to 1, and you're probably going to be correct. KD, now we're getting into the more exotic endurance limit modifying factors. KD is a temperature factor. We all know that properties of materials, or mechanical properties of materials, change with temperature. Typically, a steel gets weaker at higher temperature, right? So, what's the melting point of steel? In Celsius, not in Fahrenheit. I mean, it slightly depends on the alloy and stuff, but roughly. Is it 500 degrees C? Is it 3,000 degrees C? 6,000?
750.
It's 1,400. Right? 1,400 degrees C is a melting point of steel. So most steels, and again, it kind of depends on the alloy, but it's good to know these rules of thumb. The rules of thumb. Steel loses about half its strength at 600 degrees C. So, if you operate in an environment, I don't know, an oil refinery or whatever high temperature environment, you may have to really account for this, because if you do your calculation assuming at room temperature and then you take it into a high temperature environment, you may be really surprised about what your mechanical properties are. In fact, a few years ago I did some calculations for the refineries here in North Salt Lake, and that was welding calculations in a pressure vessel at high temperature and with really exotic alloys, and we had to really account for that high temperature. So you buy these expensive alloy materials that have ultra high tensile strength, but you put them in a 1,000-degree environment, and they're just as strong as a plain carbon steel at room temperature. So you really are sometimes surprised at how big an effect the temperature can have. This parameter is fairly easy to account for, though. Kd is equal to the yield stress at the temperature that you're evaluating divided by the yield stress at room temperature. Or if it's a brittle material, then of course we're not using the yield stress, but we're going to use the ultimate tensile strength at the temperature that you're evaluating and the ultimate tensile strength at room temperature. And so that is also shown over here in your formula sheet. You see this table. Right? And so look at the column in Celsius. So at room temperature 20 degrees C, St over SRT, the strength at temperature that you're evaluating, which is room temperature, divided by the temperature at room temperature is of course 1. And then as you increase your temperature, actually you see that your Kd factor can even be a little bit higher than 1. Right? And then as you see your temperature increases, that ratio is going to decrease. Now let's scroll down a little further here.
What's our?
See, if you go to 600 degrees C, the strength or the Kd factor goes to 0.55, right? So you see that there it loses half of its fatigue strength. This is for steel, yes. I don't know whether the table specifies that. The table does not specify that, but this is for steels. All right, we got 2 more parameters to go here. The one to last one is Ke, which is the reliability factor. Intuitively, if you want to have increased reliability, would you over-design or under-design? Over-design. So if you are requiring a higher reliability, say 99% or 99.9%, then you expect to see bigger dimensions coming out of your design calculation, right? And that's exactly what this parameter does for you. So you can say, I want a reliability of 50%, and that of course is going to give you the thinnest structures. Okay. Say if you want to have Ke equal to 1, then this corresponds according to this table with reliability of 50%, and then you see that your reliability factor decreases with increasing required reliability. What does that mean? If you decrease your reliability factor, then you will decrease sigma E compared to sigma E prime. And so that is going to result in a thicker mechanical element because you're underestimating your sigma E, right? Because you're multiplying sigma E prime with a factor that is smaller than 1. So your sigma E will be underestimated by a higher reliability, need for a higher reliability, and that will result in a higher or a thicker mechanical element. We're not going to use these very often, as you may imagine, by the speed that we're going through this, right? So, C table. And then the last parameter is this miscellaneous effects factor.